APChem students, this is Electron Configurations, which hopefully you've got a fairly good idea of from general chemistry. I think you did a decent amount of this. So again, Electron Configurations, all they are is just where are electrons located in the electron cloud. Okay, at any given time, where could they possibly be, even though they could be different areas. But this is kind of the general synopsis, I guess, or visual people think of as electron cloud. You think of these rings, even though that's really not the way it is, but it's an easy way for us to visualize it, even if it's not quite right in real life. It gives us a pretty good visualization and helps for when we start doing reactivity and bonding. So there are 7 energy levels of electrons, okay, and they are numbered 1 through 7. So you'd have energy level 1, 2, 3, 4, 5, 6, 7. Electrons obviously filling from closest to the nucleus to farthest out. Energy levels get larger as you're going out. The energy level corresponds to the rows in the periodic table. So we'll talk about that, but the rows tell you how many energy levels electrons have. Inside of energy levels, there are sublevels. So the first energy level only has an S sublevel. Second energy level has an S and P. Third energy level has an SP and D sublevel. Fourth energy level has an SP, D, and F. And then we can kind of go from there. But energy levels get bigger. Remember, S sublevels hold 2 electrons. P sublevels hold 6. So this S would hold 2, that P holds 6. That's 8 electrons at that energy level. In the third energy level, the S holds 2, the P holds 6, and the D holds 10. So that's 18. It would fill the whole energy level. Fourth energy level, the S holds 2 electrons, P holds 6. That's supposed to be 2. D holds 10, and F holds 14. All right. So if I go to periodic table, this is a little nicer than your periodic table probably. No, it's not up there anymore. I'm going to pause you for a second. We'll be right back at this. All right, back at it. Here's a periodic table. Not sure how easy that is to see. I'm going the wrong direction here. All right, moving over. So remember, the periodic table is organized according to the electron cloud. Okay, organized according to that. So the energy levels, the 1 through 7 energy levels, are represented by the numbers down the side. So hydrogen and helium are in the first row. They have 1 energy level of electrons. Okay, so for example, everything in this row would have 4 energy levels, 4 rings of electrons, or more importantly, their valence electrons are out in the 4th energy level. These elements all the way across here would have 3 energy levels of electrons. These all the way across here would have 6 energy levels of electrons. That means their valence electrons are out in the 6th energy level. So those represent the energy level. Remember, these sublevels, S, P, D, and F, have sections of the table. Okay, this is considered the S block of the table, P block from here to here. Right there is the D block of the table, and down here would be the F block of the table. Strangely enough, in the S, there are 2 rows. S's hold 2 electrons. There are 6 columns here. P's hold 6 electrons. There are 10 in the D. D's hold 10 electrons. And 14 in the F. They hold 14 electrons. So for writing a configuration, let's say we're writing the configuration of iron right here, which has 26 electrons. So I'm going to write the whole entire thing, even though we normally don't do that. So iron's 26 electrons. They first fill in the 1s, first energy level S sublevel. That's the only sublevel in the first energy level. So we go 1s, 2. Those electrons closest to the nucleus, not generally involved in much. That energy level is full. So 2 electrons, first energy level, S sublevel, that's full. We go second energy level then. So second energy level, S sublevel, and there's 2 spots for electrons. Once that fills in, we go 2p, and there are 6 spots for electrons. That fills the whole second energy level. There's 8 electrons in there, 2 in the S sublevel, 6 in the P. Come down here now. Third energy level has an S sublevel, so we go 3s, which holds 2 electrons. So we now have done 12 electrons. That'd be magnesium's configuration if we stopped right there. After 3s, working our way across, comes 3p, and there are 6 spots for electrons. That gets us to 18 electrons. Again, we're trying to work till we get to iron. After that comes 4s. things get a little out of order. Things go a little out of order. 4s comes before 3d, and all has to do with energy. Electrons want to be in the lowest possible energy sublevel. 4s is a little closer to the nucleus than 3d. It's a little bit lower energy, so it fills in first. Okay, so you just kind of have to remember that this is 4s, and then we go back, and the d section is always one less than the s out here. So 4s to 3d. If we're doing iron, we go 1, 2, 3, 4, 5, 6. So it'd be 3d6. Remember, valence electrons, or electrons in the outermost energy level. Electrons in outermost energy level. So the valence for iron would be, well, those are in the third, fourth, third. Its outermost energy level is the fourth energy level. It's got 2 valence electrons. 2 valence. If you notice here, iron forms 2 possible charges. It can be a +3 or a +2. So if iron formed a +2 charge, meaning it's lost 2 electrons, it loses those 2 electrons. Its other charge is, actually, its number 1 charge is a +3. Okay, its number 1 charge is a +3. It tends to also lose 1 from this D. Okay, from this D sublevel. It really likes, elements really want half full or full SP, D, and F sublevel. So if it loses 1 more from there, it lost 2 from there, 1 from there, and now have a +3 charge. It gets rid of that 1 electron there. So that is the full configuration. Let's do a noble gas configuration real quick, which you hopefully remember. Let's say we are doing gold. Okay, let's say we're going to do gold right here. Let's just change that. Let's do tungsten. Tungsten element number 74. So remember, we're going to pick the noble gas that comes before it. So noble gas that comes before it would be xenon. So what we're saying there is xenon's got 54 electrons, which basically fill the first 5 energy levels. Tungsten has that same exact 5 energy levels as xenon that are full, plus it has some extra beyond that. It's just the extras that usually matter. So we'll go to xenon in brackets. After that would come 6s2. That's the 55th and 56th electrons. We can't skip from 56 to 57. So we got to go down and do 4f. So remember, this is 4f and it's 14. So 4f, 14. And then we come back up. That gets us to 70 electrons. The 71st electron would be right here. And then we would go 5d. 1, 2, 3, 4. 5d, 4. Remember, valence, outermost energy level. Those are in the 5th energy level, 4th energy level, 6th. Tungsten has 2 valence electrons. Okay, 2 valence. I want to draw the orbital diagram too. So if you remember, S's have 1 orbital. I usually just draw an orbital with a line. So S's they've got 1 orbital. It has 2 electrons in it. 1 spinning clockwise, 1 with a magnetic counterclockwise spin. So remember, 2 electrons can be in an orbital. They have to have opposite spins. 2 electrons in an orbital must have opposite spins. Cannot have the same spin. And F sublevel would have 7 orbitals. So they want to fill in by themselves if possible. So there's our 14 electrons in the 7 orbitals in the F. And a D sublevel would have 5 orbitals because it can hold up to 10 electrons. Hopefully you can see this. It's a little cluttered in there, I'm sorry. So it's got 5 orbitals. It's only D4, so I'm going to go electron. I don't care if the arrow is up or down. Okay, it can be clockwise or counterclockwise when it's by itself. Electron, electron, electron. Those are the 4 electrons. They really want to be unpaired if possible. They do not want to be together. As I mentioned earlier, here's one of the weird elements. Probably did this last year, but elements like to have full and half full sublevels. So like this sublevel is full. This sublevel is full. This one's not full or half full, but it's really close to being half full. So what can happen is an electron can move from this sublevel to this sublevel. So I'm going to take this electron out of here. So this is now half full, and move that electron up to here. This is now half full. So if you look here now, tungsten would now have one valence electron. Okay? If you look at tungsten's charges, +6 and +4. +6 and +4 is 2 charges. Well, +6 would mean it probably lost this electron, and those 5 electrons would be its +6 charge. Its +4 charge would have been when there was 4 electrons here, it would lose those 4. All right? So that's the orbital diagram. There are some elements that remember make that switch to become half full and half full. Or, for example, copper, silver, gold, they will take an electron from the S, move it up, and fill their D sublevel. Okay, they'll fill that D sublevel. All right, let's do a configuration of an ion. Remember your dots as we're doing dot diagrams. So say we're doing fluorine's valence electrons. Fluorine's got 7 valence electrons. So you can put 1 electron per side and then start pairing. There's 5, 6. It's got 7 valence electrons. Pair of electrons, pair of electrons, pair of electrons, unpaired electrons. I think you did enough dot diagrams last year. Hopefully you'll be able to do that. Let's say we're doing an ion. Okay, so maybe say we're doing like let's say we're doing sulfur -2. Sulfur with a -2 charge. So here's sulfur's configuration. We'd go neon. And then after neon, we go 3s2 and 3p4. That's normal sulfur with no charge. If it has -2 charge, remember that means it has gained 2 electrons, not 3p6. That gives it its 8 valence electrons. All right. If we were doing something like scandium with a +3 charge. Okay, so scandium with a +3. So I'm going to write this whole configuration, or the last part of the configuration. So scandium, I'm going to write down, I'm going to skip some stuff, but 3s2, 3p6, 4s2, switch colors here, and then 3d1. Well, notice scandium has that +3 charge. So +3 charge means it's lost 3 electrons. Well, if you think about the 3 electrons it's going to lose, first it's always their valence. So those 2 electrons, gone, plus that electron, gone. So they've emptied out its whole outer energy level. And now its outer energy level will be the 3rd energy level, which has 8 valence electrons in it. So they will empty out to get to 8 valence electrons from there. Some of these charges get a little tough. You know, like a +7 on manganese means it's lost 7 electrons, which you can probably figure out which ones those would be. But sometimes they get a little bit weird as you're going through there. Let me do one more. Let's say we're doing aluminum with a +3 charge. Aluminum forms a +3 charge, so aluminum +3. So I'm going to write the whole configuration. There's 1s2, 2s2, 2p6, 3s2, 3p1. That's normal aluminum, all 13 of its electrons normally. With a +3 charge, it's lost 3 electrons, so that would be this electron and those 2 electrons. Those are gone. So if you look now, its 2nd energy level is now its outer energy level, and it has 8 valence. All right, that's a quick electron configuration.